Hello students, welcome back to another lecture in environmental modeling and simulation. Today we are going to continue our discussion on an imperfect bifurcation to see what happens to a symmetric system when we add an imperfection in it. The system that we have been covering so far is this one. Dx by dt, the rate at which x is changing with time, is equal to rx minus x cube plus imperfection h. And the bifurcation analyses that we have been trying to do with this is to vary r keeping h constant and vary h keeping r constant. So we have two parameters here, r and h, and whenever we have multiple parameters, we vary them one at a time to see how system behaves. To recap what we have done in the last lecture, we have figured out that when we keep h constant and vary r, our system looks something like this. So on x-axis, I am plotting r, and on y-axis, the fixed points. So let's say h is equal to 0, h is not equal to 0. H is equal to 0, we have one fixed point here. Let me choose another color. And then this fixed point, which is a stable fixed point, turns into an unstable fixed point, and we have two new fixed points. So this acts very much like a pitchfork bifurcation because the imperfection is 0. Now what happens when the imperfection is not 0? We have a positive stable fixed point that slowly approaches 0, and when r is equal to minus infinity, it will be equal to 0. We have two more fixed points which appear somewhere here at r critical. So at r critical, what we get is a saddle node kind of behavior. Remember, saddle node bifurcation is the kind of bifurcation when new fixed points appear or disappear. This, on the other hand, is pitchfork bifurcation, and it is called pitchfork bifurcation on the basis of its bifurcation diagram. It can also be called as trifurcation because this sort of resembles trident. So at r critical, two new fixed points, a single fixed point which is half stable, half unstable appears, and then as you keep increasing r, then that fixed point splits into two fixed points. One of them is stable and the other is unstable. So the unstable one approaches 0 as r tends to infinity. The stable one decreases like so. So this is what happens when we keep h constant and we vary r. Today we are going to look at what happens when we keep r constant and vary h. So this is our system. And we are going to vary h keeping r constant. So very easy, I am going to write this, in order to do this graphically, I am going to write this as a line and a curve, two functions. This is the line minus the curve. Now I am going to draw the phase portrait. These are one-dimensional systems, so we are plotting variable that is changing with time on x-axis and the rate at which it is changing on y-axis. And very soon when we go into 2D systems, phase portrait will start looking slightly different, but this will do for now. Alright, Rx plus h, let's say we are starting with a positive value of h, then h will be an intercept. Let's say r is greater than 0. So the slope is positive, looks like this. The cube function looks like this. When x is negative, x cube is negative. When x is positive, x cube is positive. So we can see that for certain value of h, so this is your intercept h. For certain value of h, there is only one fixed point. And let's look at the stability of this fixed point. On left side of the fixed point, line is above the curve. On right side of the fixed point, the curve is above the line. So on the left side, dx by dt will be positive, flow will be towards plus infinity. On right side of this fixed point, dx by dt is negative, and the flow will be towards minus infinity. So clearly this is a stable fixed point, and we are going to denote it by coloring in the circle. Now let's vary h. I am going to use a different color. As we vary h, what we will notice is that there will come a time when this line will be tangential to the curve in the third quadrant. So we still have a fixed point which is stable, positive fixed point that is stable, but a new fixed point has emerged on the negative side. So here, notice on both sides of the new fixed point, the line is above the curve, which means dx by dt is going to be positive on either side of this new fixed point, which means the flow on either side is going to be towards plus infinity. So clearly this is a case of half stable and half unstable fixed point. Now let's vary h further. What we are doing is we are reducing h. Now as I reduce the h further, there will come a time very soon now where the line will intersect the curve in 3 places. So now we have 3 fixed points. So there is a fixed point here which is a stable fixed point, because on left side the positive fixed point is still going to be stable, because on the left side the line is above the curve, dx by dt is positive. On right side line is below the curve, dx by dt is negative, the flow will be to the left. Now in the third quadrant, the line will intersect the curve in 2 places. So now we have 2 fixed points. One fixed point is somewhere here and the other fixed point is going to be somewhere here. I'm going to redraw this curve just to make sure that sort of makes sense. Okay. So we have 2 new fixed points on the left side of the y-axis. Let's look at the stability of these fixed points. So let's call this the first fixed point, the second fixed point. Third fixed point we know is a stable, so I've already colored it in. Now the first fixed point on the left side, the line is above the curve, so dx by dt is going to be positive, the flow is going to be towards right side. On the right side of the first fixed point, the line is below the curve, the dark orange line is below the blue curve, which means that dx by dt is going to be negative, the flow is going to be towards minus infinity in this direction. So we know that the first fixed point here is a stable fixed point, and to denote that, just color it in. Let's look at the second fixed point. On left side of this fixed point, the curve is above the line, which means the flow is going to be towards minus infinity because dx by dt is negative. On right side, the line is above the curve, which means x will be increasing, dx by dt is going to be positive, the flow is going to be to the right. So this is an unstable fixed point. So we have seen that as we vary h, 2 new fixed points appear. One of them is a stable fixed point, the other is an unstable fixed point. As we keep on reducing h, so let's go further and let's reduce h further. As we keep reducing h, there will come a time when h will become negative. So let's look into that. So here the h is negative, and what is happening is it is intersecting the curve on left side of the y-axis in only one place. So we have a new fixed point here, and then in the first quadrant the curve and the line are only meeting at the point of tangents. The curve and the line are meeting only at one point where the curve and the line are tangential to each other. So clearly 2 fixed points have merged into one. So we have one fixed point here, and we can very quickly find out the stability of this fixed point too. For the first fixed point here, let's call it first, let's call it second fixed point. For the first fixed point here, on the left side the line is above the curve, so the flow is towards plus infinity. On right side the curve is above the line, so clearly we can see the flow is towards the fixed point. This is a stable fixed point. Now the second fixed point that we have here, on the left side the line is below the curve, so the flow is towards left side, and on the right side the line is below the curve, so again the flow is towards left side. So this is a half stable, half unstable fixed point. Let's vary h again, let's reduce the h even further, and now we have only one fixed point left. On the left side of the fixed point, line is above the curve, right side line is below the curve. So by now you already know that this is going to be a stable fixed point. So we see first we had only one fixed point, and then 2 new fixed points emerged, and then 2 fixed points merged into one, and then we were left with only one fixed point. So let's draw the bifurcation diagram where r is positive, and we are varying h. So since this is a bifurcation diagram where we are keeping r constant, we are keeping the slope of the line constant, we are going to plot the parameter h on x-axis and fix points on y-axis. So let's start with a big enough value of positive h. So we start with a big enough value where we have only one fixed point, which was this case, by the way. So we have one fixed point and it's a stable fixed point. So here we have one fixed point, h is big enough, it's a stable fixed point. Then as we reduce h, there comes a time when two new fixed points emerge and one new fixed point emerges and that fixed point is a negative fixed point. And as we are reducing the value of h, this fixed point, the first fixed point, is moving towards left side. It is slowly reducing. So what we'll have is that this is slowly reducing, not very rapidly, slowly. And once it reaches a particular value of h critical, the line will become tangential to the curve in the third quadrant. So new fixed point emerges here. Now, as we keep reducing h, what will happen is that we'll have two fixed points in the fourth quadrant in this diagram, bifurcation diagram, which here is denoted by the dark orange line. Let me clean this up a little bit for you. So this is denoted by the dark orange line here. So we notice here that we have two fixed points. The smaller fixed point, the one that both are negative, the smaller fixed point is a stable fixed point. The other fixed point is an unstable fixed point. And this is happening as h is reducing. So what will happen is as h reduces, we have a fixed point that comes like this, and then we have an unstable fixed point that goes like this. Now, again, I do not know if at this moment, I do not know if this unstable line will meet the center of the coordinate axis yet. How we are going to figure it out is find out the fixed points when h is 0. So when h is 0, this fixed point, the unstable fixed point, will be at the center of the coordinate axis. So now I know it will meet the center of coordinate axis. So this is how it looks like. Now keep reducing the h. As I keep reducing the h, now my line is represented by this lighter color blue line, and what I can see is that this fixed point and this fixed point here, they will merge into a single fixed point. So we know that as we reduce h and we reduce it to particular critical value of h, so here we have reached the second critical value of h, and it's negative critical value of h critical. What will happen is that these two fixed points, this one and this one, will merge together. And this fixed point, which is the smallest fixed point, will keep getting smaller slowly, but will remain stable. So this is how a bifurcation diagram looks like when we are keeping r constant and r is positive, and h we are changing. Okay, this was the case when r is positive. Let's look at what happens when r is 0 or less than 0. So again, our system is dx by dt, rx minus x cube plus h, which I am rewriting as rx plus h minus x cube, line minus curve. The curve looks like this. And I'm talking about a situation when r is less than or equal to 0, right? We are varying the h. So when r is less than or equal to 0, the slope of the line is either 0 or negative. So let's start with the negative line. Let's say h is positive. Now if h is positive, we'll see that the line and the curve will intersect at only one place. This is h, by the way, the intercept. On the left side, the line is above the curve, so dx by dt is positive. The flow will be towards plus infinity. By now, you have gotten a hang of it. And if you have been following the assignments, you know how to figure out the stability of your fixed points. This is going to be a stable fixed point. Now, let's keep varying h. As I vary the h further, I'm reducing. Still have one fixed point, and it's a stable fixed point. Keep reducing h. Still have one fixed point, and it's a stable fixed point. So as I change h value from a very positive number to very big positive number to a very small negative number, we still get only one fixed point when r is less than 0, and it's a stable fixed point. Now let's look at what happens when r is equal to 0. So the slope is 0. So we have a horizontal line. So here is the curve, And now we have a horizontal line. For positive edge, we have one fixed point, and you know by now this is a stable fixed point. Now, as we reduce the edge, bring this line down, we still manage to have only one fixed point at all times, and these fixed points are also stable fixed point. So our bifurcation diagram becomes very easy. It looks like this. So let's, because we are varying h, we'll put h on x-axis and we'll put fixed points on y-axis. In this case, r is less than 0 or equal to 0, quite similar behavior. So we can put them all together in r less than or equal to 0. Now we have one, when h is positive, we have a positive fixed point and it reduces as h reduces. So it reduces as h reduces. When h is equal to 0, then the fixed point is 0. And then as the h reduces to a negative number, the fixed point also goes negative. And this is forever stable fixed point. So there is no bifurcation happening here. But this is how your bifurcation diagram will look like. No particular kind of bifurcation happening here. Now, so this is how we see how when we vary h and keep r constant, how our system looks like. When we keep h constant and vary r, how our system looks like. And now there has to be a way to put them together. So if you are somebody who likes to visualize in 3D, you can make a 3D diagram, which is where actually you can see why imperfections are so important for catastrophes. So that's why I want to dive into a 3D diagram. 3D diagrams can be very hard to draw. So what I'm going to do is I'm going to share a picture with you. So in this 3D diagram, what we'll do is we'll have r on one axis, we'll have h, the second parameter, on another axis, and we'll have fixed points on the z axis. And we'll see how our system varies. So let's take a look at the 3D diagram, and I have a picture for you because 3D is incredibly hard to draw. So in 3D, this is how our bifurcation diagram will look like. So on x-axis here, we have parameter h, on y-axis we have r, and then on z-axis we have our fixed points denoted by this particular character. And on z-axis we have our fixed points which are denoted by this particular character. Okay, so how do you interpret this diagram? Visually, as you look at it, you can see that for a certain range of r and h, we'll have a dramatic change because of this fold. You see this fold? So let's say we have a fixed point here and we have some fixed points here for a given value of r and h. And as we are varying the r and h, the fixed points will stay quite reliable. So the fixed points that we have here are quite reliable, but then suddenly this fixed point, which is here on the top of the surface, will undergo a sudden drop. So this sudden drop is where catastrophes happen. This is where extinction events happen. There is a sudden drop in the change in the number of species. There is a sudden change in the chemistry, biogeochemistry of a location. On the other hand, it is quite possible that the reverse may also happen. The reverse may also be true. Now, if we vary the r but keep the h constant, let's say we are starting from here, right? We're varying the r but we're keeping the h same as here, and now we start undergoing a similar change, we will not see a catastrophe. So together, if we modulate the parameters, we will see that the behavior can be a gentle change in the system's behavior, or we can see sudden fall in a particular fixed point, or sudden disappearance of a particular fixed point, where catastrophes or outbreaks happen. So if we are going from left side to top, then we will have a situation where we are undergoing a sudden increase because a new fixed point has appeared here and it is much bigger than the fixed points that were here. But if we are going from this position to here, then we'll see a sudden drop. The other thing I want you to look at is, remember the 2D diagrams that we made of fixed point versus one of the parameters h or r, you can derive them from here. So let's say you have a particular value of r. So r is on this axis. So let's say you have selected this particular value of r. Now you vary your h. So when you vary your h, you will be intersecting the surface that we have here. And how will that surface looks like? That surface will look like this when you kept the r constant and varied h. So you will see either this surface depending on the value of h, this kind of bifurcation diagram, or this kind of bifurcation diagram. So you can see here very clearly that here you will probably see a bifurcation diagram like so, but here you will get a bifurcation diagram that looks like this. Similarly, if you keep h constant and then vary r, you can again do a cross section of this surface and you will get the same bifurcation diagrams again. Now we will move on to another model, which is a catastrophe model, and in this catastrophe we see a sudden increase in the population of a particular insect, and we will notice that the bifurcation diagram looks very similar to this bifurcation diagram, and that we are going to look into. The model that we are going to look into is that of insect outbreak. Before I get into insect outbreak, I want you to think about this. How do we define insect growth versus insect outbreak? So when do we say that yes, this particular insect that we are noticing, that we are following is growing in the particular system, ecosystem, and when do we use the phrase outbreak? Now, I want you to pause this video and think about it for a few seconds. Okay, I hope that as you thought about how do we as mathematicians, as engineers decide when a particular system is undergoing an outbreak versus normal growth, it has to do something with the magnitude of change. If the change is abrupt, if the change is rapid and of a bigger magnitude, then we might want to call it an outbreak. But if it is a slow gradual increase, we might want to call it growth. But again, this particular understanding of growth versus outbreak is also not very specific, because let's say a particular insect or a particular bacteria is undergoing exponential growth. So there might come a time during the exponential growth phase where the increase in number of that particular insect or bacteria will be very rapid. Does that quantify now as an outbreak, or does that quantify as growth? So, and the problem is that if you're talking about an insect that feeds on, let's say, leaves, right? Then the leaves, they take much longer time to grow, and insects take much shorter time to grow. So again, how do we compare these two time scales? A shorter time scale of plants and trees, a longer time scale of plants and trees, and a shorter time scale of insects that are growing. So one way to answer this question between outbreak and growth is to non-dimensionalize everything. And why is this important? So let's say I'm looking at the outbreak of insects. So insects multiply very rapidly, and there are some insects, when they lay eggs, one parent can produce multiple offsprings, and given the right circumstances, many of them may be able to survive long enough to damage our crops, our forest. Now, if you're looking at disease outbreak, it is quite possible that the disease might have a longer incubation time, may take longer time to show symptoms and to be registered as disease. So it's quite possible, depending on whose growth or outbreak we are following, the time scales will vary a lot. So we need to standardize this, we need to non-dimensionalize this. This is a very important instance where dimensional scaling and analysis is very important. If you remember it from a previous lecture, to do dimensional scaling, you need to non-dimensionalize all variables and all parameters. And we are definitely going to do that when we do our insect outbreak model. The insect outbreak model that we are going to cover in the next lecture was actually first written in 1978 by a mathematician called Ludwig. The insect that he was looking at is spruce birdworm, which eats a particular kind of fir tree leaves. Now, I'm going to teach you this insect outbreak model in the next lecture, but do take time between this lecture and the next to think about how you're going to model this. We are going to use almost exclusively the concepts that we have covered so far. Basically, we are going to write a function where we have a net growth rate, and then we have something external to the net growth rate, the usual growth minus death rate of the worm, something else that is causing death or increase in the number of the worm. In this case, this particular worm is eaten by birds, so we are going to talk about predation. X is the number of insects. Alright students, this is all for this lecture. Let's meet in next lecture where we'll go through the Ludwig's model for insect outbreak. Thank you.